Hi, welcome to Algebra 2 Common Core. Today we're going to talk about solving exponential equations using logs. You're going to find that this is one of the most useful techniques in Algebra 2, especially with exponential equations. So let's go back and review our logarithm law for exponents. Remember that whenever we have a log, so it might look like this, log to the base b of something raised to a power. We can always take that power and make it the coefficient because we're really talking about multiplying exponents together. So our answer here would just be p times the log to the base b of m. We are going to use this technique multiple times today. So for exercise number 1, we want to solve the exponential equation 4 to the x equals 8. There are two ways to solve this equation, one that we already are familiar with. That's called the method of common bases. So when I look at the equation 4 to the x is equal to 8, I'm looking for what base I can write both 4 and 8 in terms of. Of course, that's going to be a 2, so 4 is written as 2 to the second power. But we're going to raise that to the x. 8, of course, is written as 2 to the third power. Remembering what we've done in the past, we multiply the exponents on the left, set it equal to the exponent on the right because the bases already match, and we get that my exponent should be 3/2. Now if you test that out, that of course makes sense because 4 to the 3/2 means take the square root of 4 and then cube it. Square root of 4 is 2. 2 cubed does give me 8. So I see that that checks, and my answer is x equals 3/2. Now, let's take a look at a new technique that we're going to learn about today. This is using a logarithm. So if I'm starting with my equation 4 to the x is equal to 8, what I can do to this equation is take the log of both sides. As long as I'm doing the same thing to both sides of the equation, then I'm going to preserve equality. So I've got the log of 4 to the x is equal to the log of 8. So you'll notice that I took the log on both sides. Now, remembering our rule for exponents that we just talked about above, we see that because the 4 has an exponent of x, that exponent can be moved down in front, so I now have the coefficient x, log of 4, equals log of 8. Now you'll notice that I'm not writing a base on my logs. That's because I'm using a common log right now where the base is assumed to be 10. So when I go to my calculator, I'm just going to be using the log key on my calculator, which is just to the left of the 7 key on the calculator. So in order to solve for x, I'm going to divide both sides of the equation by log of 4. Notice that I'm not dividing 4 into 8. What I'm doing is dividing log of 8 divided by log of 4. So I'm now going to go to my graphing calculator. I'm going to use that log key, and when I do that, I'm going to say log 8. Make sure you close the parentheses after the 8, and then divided by log 4, and again close the parentheses. When I do that, I see that my calculator gives me 1.5 for the answer, which of course is the same as the answer that I got previously when I used the method of common bases. So my answer is 3/2. So you'll see that with this approach, we don't have to have numbers on either side that can be written with the same base. So that's going to be an extremely useful tool for us, especially when we're solving application problems. So let's review the steps that are going to be necessary to solve an exponential equation with logs. It may be necessary for you to pause the video as we go through these steps so that you have time to write them down. So step number 1, we want to make sure that we are isolating the exponential on one side of the equation. So if the exponential is not already by itself, then we've got to do mathematical operations in order to get the exponential by itself. We might have to do subtraction or division so that the exponential is isolated. Step number 2, we're going to take the log on both sides of the equation. And again, when I'm talking about taking the log on both sides, in these examples, I'm taking the common log. So that's log to the base 10 so that I can use my calculator to solve. Step number 3, once we've taken the log on both sides of the equation, we want to use the exponent rule so that we can bring the variable down as a coefficient. And step number 4, it may be necessary to again do some arithmetic operations to get the variable by itself and solve for the answer for x. So you're going to use your calculator to solve for x. Be sure that you've got your graphing calculator right by your side today because we're going to be using it throughout this lesson. Now if you need some extra time to write down those steps, pause the video and come back when you're ready to try a couple more examples. Let's move on to some examples here. So I have the exponential equation 7 to the x is equal to 52. Now clearly 7 and 52 cannot be written with the same base. So I have no other way to solve this equation other than taking the log on both sides. So I'm going to rewrite this and say log of 7 to the x is equal to the log of 52. Now because I've got an exponential here, I'm going to move that exponent x as the coefficient. So x log of 7 equals log of 52. And then I'm going to go to my calculator, but first I want to divide both sides by log of 7. So on my calculator I get that x must be equal to log of 52 divided by log of 7, and again don't forget to close parentheses on each number after the log. This gives me the answer 2.03. Now these are super easy to check because all we have to do is go back to our original equation, and on my calculator I'm going to type in 7 raised to the, so use that caret key right above the division sign. Try out my answer, 2.03 for the exponent, and see how close you get to the answer of 52. Now, of course, it won't be exactly 52 because this is a rounded answer that we're giving. So right now I'm rounding this to the nearest hundredths. Why don't you take a minute and try example number 2. So to solve this equation, I took the log on both sides. So log of 3 to the x equals log of 5. Using the exponent rule for logs, I brought the x down to be the coefficient of log of 3. And then I divided both sides of the equation by log of 3 and rounded my answer to the nearest hundredths, so I got 1.46. For number 3, we're going to do the same thing. We've got 9 to the x is equal to 140. And again, I see that there's no way to solve this equation using common bases. In fact, we find that this logging approach will work on any equation. Even if you can do common bases, you're allowed to solve by logs. So this is a really important method to learn. So I'm going to take the log on both sides. So I've got log of 9 to the x is equal to the log of 140. Bring the exponent down, so x log of 9 is equal to the log of 140. And then get the x by itself, so x is equal to log of 140 divided by log of 9. Go to your calculator, and again, you cannot do this without your calculator. And I'm rounding to the nearest hundredth, so I've got 2.25. Now if you go back and check, 9 raised to the 2.25, see how close it is to 140. Why don't you take a minute to try example number 4. So I took the log on both sides of the equation, allowing me to bring the x down in front of log of 5. Then I'm going to divide both sides of the equation by log of 5 to get the x by itself. Make sure that you don't do the logs and round those answers. Go ahead and put the whole division into your graphing calculator so that we're not doing any premature rounding. So that's how I'm getting the answer of 2.04. And again, go back and check it. That answer definitely makes sense because we know that 5 to the second power is equal to 25. So therefore, we've got to be just a little bit bigger than 2 for my exponent to get an answer of 26.8. Now, before you turn the page, I want to talk about what happens when I've got an equation that has an e in it. So maybe at the bottom of page 13 you can fit this in. So if my exponential looks like this one, e to the x equals 67, I notice that my base is that irrational number e that we learned about in the last lesson. So instead of taking the log of both sides of this, we're going to do a different operation, very similar, but we're going to take the natural log on both sides. We want to take the natural log on both sides of the equation because natural log and e are inverses of each other. So notice what this is going to look like. The natural log of e to the x is equal to the natural log of 67. Now when I bring the x down in front, I've got x natural log of e equals natural log of 67. Now let's recall that natural log really just means log to the base of e. So I know that that answer, natural log of e, is actually just a 1. So right now I have x times 1 equals the natural log of 67. So all I need to do to solve this is to go to my calculator, use the natural log key, which is right below the log key. And when I do the natural log of 67, I get that x is equal to 4.2. And again, we're going to check that by doing e to the 4.2 and making sure that we get close to 67. So you'll see that when I have an e equation and I use natural log to eliminate, then actually the process is a lot simpler. I think I'm going to skip over example number 5 because it's so similar to the ones that we've done before. Let's go ahead to example number 6. For example number 6, you see that we've got 8 times 10 to the x. So this time the exponential is not by itself. I need to do some arithmetic to get the exponential by itself, so I'm going to divide both sides of the equation by 8. So I now have the equation 10 to the x is equal to 200. Now this time it worked out to be a nice whole number. It won't necessarily always do that. Let's take the log on both sides of the equation. So log of 10 to the x is equal to log of 200. Bring that x down in front. So x log of 10 equals log of 200. And then we're going to divide both sides by log of 10. So x is equal to log of 200 divided by log of 10. And this is where we need our calculator. And it turns out, when I did this on my calculator, I got an answer of 2.30. And again, go back and check in your original equation. For example number 7, we still want to get the exponential by itself, so let's subtract 5 from both sides of the equation. So the opposite operation, or the inverse operation, would be subtraction. So I now have 15 to the x is equal to 35. Again, can't write these both with the same bases, so we're going to take the log on both sides. So I end up with log of 15 to the x equals log of 35. Move that x down in front, and I think we're getting good enough that we can just say, oh, x is going to be equal to the log of 35 divided by the log of 15. When I do that calculation on my calculator, that came out to 1.31. Take a minute to try example number 8 and then come back and check your work. check your work with my work, I had to divide both sides of the equation by 6, first of all. Make sure you never multiply that 6 times that 3 because 3 has an exponent and 6 doesn't. So we wanted to divide both sides by 6, and then we follow through exactly the same way by logging both sides of the equation, moving the exponent down as the coefficient, and dividing both sides of the equation by log of 3 to get an answer of 3.15. Now, where we're really going to see this method as helpful to us is on our application problems. So up until now, we've been using our calculator and looking at the table of values or finding an intersection point using our graph on our calculator. However, if the problem says that you have to solve it algebraically, then you're going to have to show the algebraic work of taking logs on both sides. So depending on whether the question specifically tells you you have to do it algebraically, you are still allowed to do the graphical approach as long as it doesn't specify the method. So for exercise number 2, I've got that a biologist is modeling the population of bats on a tropical island. When he first starts observing them, there are 104 bats. So obviously that's a really important number to put into our problem. The biologist believes that the bat population is growing at a rate of 3% per year, and we see that we've got exponential growth. So let's make our equation. Maybe pause the video and see if you can think about what the equation is going to be for the number of bats, B of t, where t stands for the number of years. Now, here's the equation that I came up with. Since I've got exponential growth, my initial value goes in front of the 1 plus r value. So 1 plus 0.03 raised to the t. I'm going to simplify that, so I'm going to say b of t is equal to 104 times 1.03 raised to the t power. So there's my answer for the equation. Now, if I want to use this equation, and again, notice that this problem specifies that I have to solve it algebraically, for the number of years that it will take for my bat population to reach 200. So again, we're going to have to use our calculator on this and set our b of t equation, 104 times 1.03 to the t. We want to set that equal to 200. Now when I do that, this is an example of one where I've got to get the exponential by itself. So I'm going to divide both sides by 104. Now of course you're going to see most of the time here that these numbers don't go in evenly. So I'm going to say 1.03 to the t is equal to, and I'm going to have that number on my calculator. When I write it down, I'm going to write 1.92307 ... showing that there's a lot more to that number. But I'm going to use the unrounded version when I do the calculations in a couple minutes. So I'm going to take the log of both sides, and when I do that, I'm going to move that t out in front. So the log of 1.03 multiplied by t is equal to the log of that number that I just got when I did the division. And again, showing ... Get the t by itself, so we're going to say the log of that quotient, 1.92307 ... divided by the log of 1.03. Now to enter this on my calculator, because I want to do the log of the previous answer, I'm going to hit the log key, and then I'm going to press second answer, which is the second negative sign. Close the parentheses because we want to take the log of that answer and divide it by the log of 1.03. So when I do that division, I got 22.1 years. I hope you're seeing how much easier this is than creating a table of values or looking on my graph. But of course, both of those methods are still really useful methods if the problem doesn't specifically say algebraically. We can definitely go back and put that 22.1 years in for t into my equation so that I can go ahead and see if I'm up to 200 bats. The next application problem has to do with money, but this time, unfortunately, our stock value has been declining. So declining means I've got exponential decay. It's declining at 5% per week. So if I'm starting out at $22.50 per share, we want to determine algebraically the number of weeks that it will take for the price to reach $10. So let's start by writing an exponential equation that represents this stock price. So I'm going to use S of t for my stock price. I'm starting with a price of $22.50. Because I've got decay, I'm going to say 1 minus my rate. So 1 minus 0.05 raised to the t. Go ahead and do that calculation. So S of t is equal to $22.50 times 0.95 to the t. Now we want to take that equation, S of t equals $22.50 times 0.95 to the t, and we want to set it equal to the stock price that we're looking for, $10. This also requires us to divide both sides of the equation by $22.50 to get the exponential by itself. Now this time when I take a look at the number, it turned out to be a repeating decimal. So technically that number is rational, so I could even write it as a fraction. But I'm going to keep it as a decimal in my calculator, and again I'm going to specify that that number keeps going by writing 0.444 ... Let's take the log on both sides of the equation, so log of 0.95. I'm going to go ahead and move the t as my coefficient, equals the log of 0.444 ... Divide both sides by log of 0.95. So that's going to be the log of 0.444 divided by the log of 0.95. And I see that it takes me 16 weeks for that stock price to go down to $10. This one said round to the nearest week, so I know that I can put 16. I could also check on my graphing calculator and look on the table of values. It's always good to have a second method to reinforce our answer. Now for my last example, you're going to have to add this to the bottom of page 14 in your notes. So this time I've got an exponential function, and let's pretend that this happened to be an application problem, and we want to solve for our x. So the equation is 4e to the 0.25x equals 200. So again, I see that I'm going to have to get the e by itself. So let's divide both sides of the equation by 4. So I have e to the 0.25x equals 200 divided by 4 is 50. Now recall that when we have e as our base, we're not going to log both sides. We're going to natural log both sides of the equation. So that then allows me to take my exponent. Now be careful here because my exponent is not just an x. I've got to take that whole exponent and move it down in front. So I have 0.25x times the natural log of e equals the natural log of 50. Remember again that the natural log of e is just 1, so right now I have 0.25x equals natural log of 50. So on the left side, I don't have a log in this equation. So when I try to get the x by itself, I'm going to divide both sides of the equation by 0.25, not the log of 0.25. So in my calculator, I'm typing in natural log of 50, close parentheses, then divide by 0.25. And when I did this on my calculator, so you do it on yours and make sure that you're entering this correctly, I got 15.65. It's been great working on log equations today, or actually exponential equations that we use logs to solve. As I said earlier, this is a really important skill in this unit, and it's going to be so helpful for us to solve all the application problems that are coming up in the next 2 days. So really make sure that you understand this concept of logging both sides. so that we can solve for an answer for an exponent. Have a great night, and we'll see you in class.